In the previous videos, we covered motion in a straight line, rectilinear motion, motion in a straight line, kinematics, force and motion, work and energy, and impulse and momentum. So let's now move on to angular motion. In this video, we take a look at angular kinematics. An object is moving in a circle is said to be undergoing circular motion, whereas an object rotating about an axis is said to be undergoing rotational motion. Regardless of whether you have circular motion or rotational motion, we take a look at these two kinds of motion in terms of angle traversed. Hence, we have what is referred to as angular motion. So, consider an object moving in a circle of radius r. The object moves from initial position, say, to this position. So, final position. So, initial position, final position, traveling distance x. So, there is displacement, change in the position of the object. If we take a look at that displacement, in terms of angle theta, you have angular displacement. Change in the angular position of the object. Say, the angular position initial is 0 and final position, you have angle theta, so final angular position is theta. We can relate theta with x. X is basically the distance traveled by the object. Basically, it's the arc length, part of the circle being traversed by the object. So you have arc length x. Geometry tells us that arc length is just equal to theta r, where theta must be in radians. And again, r is the radius of the circle being traversed by the object. Transferring r to the other side, you have theta is equal to x over r. For an object moving in a circle, there are two possible directions. The object may be moving in a counter-clockwise direction, or the object may be moving in a clockwise direction. If we designate one direction to be positive, the other direction will be negative. So putting in direction in the equation, we have plus minus sign, plus for positive direction and minus for negative direction. Thus, we have angular position. Angular position theta is equal to plus minus x over r. Angular position, that's a vector quantity. There is an arrow or bar above the variable. So, theta is equal to plus minus x over r. Again, plus minus designates the direction of the angular position of the vector, plus for positive direction and minus for negative direction. If we take a look at how fast the angular position is changing, we have angular velocity, the rate of change of angular position with respect to time. And calculus tells us that rate of change with respect to time is just d over dt, differentiation with respect to time. So we have angular velocity, omega. Omega is equal to d theta over dt, differentiation of theta with respect to time. You have rate of change of position with respect to time. We can also look at this equation in terms of d theta divided by dt, very small change in theta, divided by very small change in time. So you have angular velocity is equal to d theta over dt. If we use the equation for theta, theta is equal to plus minus x over r, and differentiate this with respect to time, we get plus minus v over r, where v, the speed of the object as it moves in the circular motion in the circle, v is the tangential speed of the object. Getting the average of this equation, you have average angular velocity, and it's just equal to theta divided by t. So you have basically position divided by time. You have radians divided by seconds. So unit for angular velocity is radians per second. Next, we have angular acceleration. If we take a look at how fast the velocity, the angular velocity of the object is changing, we have angular acceleration, the rate of change of angular velocity with respect to time. And angular acceleration alpha, again, vector quantity, there is an arrow or bar over the variable. Alpha is just equal to d omega over dt. Differentiation of omega with respect to time, or simply d omega divided by dt, very small change in velocity, in angular velocity, divided by very small change in time. So alpha is equal to d omega over dt. You have angular acceleration. And if we use the equation for angular velocity, plus minus v over r, and differentiate this with respect to time, we get plus minus a over r, where a is the tangential acceleration magnitude of the object. The tangential acceleration magnitude of the object as it moves in a circle, or as it rotates about an axis. Unit is radians per second squared. You have radians per second divided by seconds, so you have radians per second squared. So you have angular position, theta, angular velocity, omega, and angular acceleration, alpha. Whether you have angular position, angular displacement, angular velocity, or angular acceleration, the plus-minus sign refers to the direction of the vector. Plus for positive direction, minus for the negative direction. By convention, the positive direction, the plus sign, the positive direction of the motion is the counter-clockwise direction, whereas the negative direction is the clockwise direction. So again, positive direction of the motion is counter-clockwise direction, and the negative direction is the clockwise direction. Just like in kinematics, the type of angular motion an object will experience will depend upon the acceleration of the object. In particular, the angular acceleration of the object. Depending on the angular acceleration of the object may experience uniform circular motion, uniform angular motion, or non-uniform angular acceleration. An object will experience uniform circular motion when the angular acceleration is constant at 0. So alpha is equal to 0 and it is constant at 0. For uniform circular motion, you only have one equation basically to take note of. Since the acceleration is 0, the rate of change of angular velocity is 0. The angular velocity is not changing, therefore the angular velocity is constant. Omega is equal to d theta over dt. For constant omega, d theta over dt reduces to simply theta divided by t. So omega is equal to theta over t. The angular velocity is constant, therefore the initial angular velocity, the final angular velocity, the average angular velocity are equal. So you only have theta over t as the equation for angular velocity. For a more complete picture of uniform circular motion, you might want to look into the concepts of centripetal force and centrifugal force. Centripetal and centrifugal forces are often discussed in textbooks under the topic of uniform circular motion. So uniform circular motion, the angular acceleration is constant at 0. If the angular acceleration is constant but it is not equal to 0, so it's equal to a non-zero value, you have uniform angular acceleration. And for uniform angular acceleration, you have four equations to choose from. You have four equations by which you may analyze the situation or problem. You have final angular velocity, omega f, is equal to initial angular velocity, omega I, plus angular acceleration alpha times time t. So omega final is equal to omega initial plus alpha t. And then you have angular displacement or final angular position. Angular displacement theta is equal to omega initial t plus 1/2 alpha t squared. And then you have omega final squared is equal to omega initial squared plus 2 alpha theta. And then you have average angular velocity, omega average is equal to the average of omega final and omega initial. So omega final plus omega initial divided by 2. Omega average is also equal to theta over t. And finally, if the acceleration, the angular acceleration is not constant, you have non-uniform angular acceleration. For non-uniform angular acceleration, you have to go back to our basic definitions of angular acceleration and angular velocity. Alpha is equal to d omega over dt, and omega is equal to d theta over dt. And depending on the problem or situation, you might either have to differentiate or integrate. You may have noticed that for uniform circular motion, uniform angular acceleration, non-uniform angular acceleration, the equations are familiar. That's because if you go back to your motion in a straight line kinematics, to your rectilinear kinematics, you will find equations of the same form. You will find similar equations. V is equal to dx over dt. Omega is equal to d theta over dt. A is equal to dv over dt. alpha is equal to d omega over dt. Non-uniform acceleration, non-uniform angular acceleration. Uniform acceleration, for linear motion, you have uniform angular acceleration, for instance, and the equations are similar in form. The variables are different, but the equation form is similar or are similar. For instance, for uniform acceleration, you have V final is equal to V initial plus AT. You have, for uniform angular acceleration, you have omega final is equal to omega initial plus alpha t. And the same goes for the other equations. For uniform circular motion, you have uniform motion, V is equal to x over t. Uniform circular motion, you have omega is equal to theta over t. So the equations are similar. The form of the equations are similar. The only difference are the variables. You have x, v, and a for motion in a straight line. You have theta, omega, and alpha for angular kinematics. The equations are similar, so all you need to do is just remember your motion in a straight line equations, and just replace the variables by their rotational or angular counterparts, and you will have the equation for angular kinematics. Theta is the angular counterpart of x, omega is the angular counterpart of v, and alpha is the angular counterpart of a. So just replace x by theta, replace v by omega, and replace a by alpha. You would have the angular kinematics equation. Of course, if you can also memorize the equations for angular kinematics at the same time, memorize the equations for motion in a straight line kinematics if you want to. And that's it for now. That's it for our discussion of angular kinematics. In the next video, we'll take a look at a few examples covering angular kinematics. So again, that's it for now. Thank you for watching.